let me start the session. So, yeah, 1 second, let me share the screen. Is the screen visible? Sandeep sir? It's visible now? Okay. So should I start? Okay. Yeah, fine. Yeah, so the topic for today's session is SVD and its applications. So myself, Dr. Jatin Majithia, it's an autonomous institute under Ministry of Education, and it's an institute of national importance. Just on a lighter note, I came across this. So knowledge is to say something. Knowledge is not free. You need to pay what? Any rough guess? Okay, let me answer. Okay, so yeah, so the topics that I'm going to cover, or the agenda for today's session, is introduction to SVD. What is SVD and how to find it? We're going to see an example, and then we will see some properties along with some applications. Okay, so SVD is one of the very important topic in today's world, or I would say in last couple of years, or I would say by the time AI, ML, and all these things have started getting importance, along with that, SVD has also gained a lot of importance. Reason being, you can say, in today's world, we are in the world of a data, and we transfer the data, and when we transfer the signals, so like censoring and the data transfer is very important in today's world. And whenever you want to transfer something, converted into numbers, and the best way to represent numbers is in the form of a matrix. Okay, so that's why matrix are played. Play a very important role in today's world. And whenever we have a matrix, we want to transfer the numbers which are represented in the matrix form. It's not possible as in it's very risky to transfer the whole of a data in a matrix at one shot, because there is always risk of losing a data. Okay, so for example, even if you take a single image, you have an image over here. Okay, suppose it consists of 1000 by 1000 pixels, 1000 by 1000 pixels. Okay, this is of order say 1000 by 1000 pixel matrix, right? So how many entries are there? There are 1, 2, 3, 4, 5, 6. There are 1,010,000 entries are there. And if it's an image, it consists of 10 million small squares. Okay, and for each color there is a color code. For each color there is a color code. So you have a pixel matrix, and there are 10 lakh entries over here. So if you transfer 10 lakh entries at one shot, as I said, there's a high risk of losing the data. So how the data is sent? So for example, if a satellite wants to send an image to Earth, how do they send the data? So they don't send the data at one shot. They always send the images or the data in packets. Okay. If you have seen, I don't know whether any of you have seen the live streaming of NASA, NASA, when they send the image, slowly the image keeps on getting clearer and clearer. Initially the image is blurred, and then it keeps on getting clearer. The reason being, the data is sent through packets thanks to SVD. We will see this in detail maybe after some time, once I will start with the properties. But what I want to say is, it helps us in sending the data in packets, which is the need of today's hour. Okay, so that's and all those stuff that we are going to see in some time. But yeah, ultimately, what is SVD? It is nothing but, if I want to say, it is nothing but a decomposition of a matrix. Now, in many, like in your in our 11th or 12th standard, we study a very basic decomposition. Like if you take any term, but the limitation to this is our for non-square matrices, and most of the times we have non-square matrices, so we cannot use this as a decomposition. Then when you go to engineering, we study, or some people also call it as a diagram. Can anyone would like to volunteer and say what are the limitation for this? Can we do this for all matrices?
No, we can't do anything.
So yes, we can't do. Not for all matrices. The first thing is it has to be a square value should exist, and moreover, if the eigenvalues exist,
There is one to.
Yes, correct, madam. So your AM should be equal to GM for all the eigenvalues. So diagonalization is also for some limited square matrices and not for all the square matrices. So that's why this is a good decomposition, no doubt. But yeah, we cannot use for all the matrices, especially for not for non-square matrices. Then after that, we study Jordan decomposition. After diagonalization, we have Jordan decomposition or triangularization. Right? It says that your A can be written as P J is the Jordan block or the Jordan matrix. Again, here we have the limitation that this has to be again one is the characteristic polynomial should split into linear factors. Okay, so only then one can have the Jordan form. But then again, among this, the good is rational canonical form, because you can any square matrix can have the rational canonical form. Okay, you can write it as a block diagonal representation. But as I said, all of them then has to need a square matrix. But then what if you have a non-square matrix? And that's where SVD comes into the picture. Okay, so SVD. So what does SVD says that if you have any non-square matrix, A is a matrix of order say m cross n, okay, then your A can always be decomposed. Always, I'm saying always, no conditions. It can always be decomposed as the product. These are very nice matrices. My V is an orthogonal matrix of order m, and my sigma is a matrix of order m cross n. One can see it's a kind of, you can say. Then this is an SVD decomposition. Okay, so what I want to say is, if you have a matrix m cross n over here, the first one is a square matrix, which is an orthogonal matrix of order m. Then you have kind of diagonal, which I will represent by sigma 1, sigma 2 up to sigma r, and then 0, 0, 0 here, 0 here, something. Let me not write 0 here. This is a matrix of order m cross n. And then we again have an orthogonal matrix of order n. And these sigma i's are called as the singular values. One can Google why the name singular. And as a best practice, we always arrange them in the decreasing order, or I will say non-increasing order, because I'm writing greater than or equal to. Okay, we will see corresponding to this stores lots of information. Okay, we will see during applications. So that's why this is the usual trend that we write in a non-increasing order. I hope everyone know what is an orthogonal matrix. Would anybody would like to put a light on this? when you say matrix is orthogonal? Anyone? Any wild guess?
A transpose is equal to identity.
Correct. So when your A into A transpose is identity, or the inverse matrices, no, people are happy when they have orthogonal matrices. Why? I will tell you. Because suppose if you have a matrix of order, say 1 billion cross 1 billion, okay, and if I ask you what is the inverse of this matrix, it will take hell lot of a time, because I mean, okay, I should not use that word, because it's a 1 billion cross 1 billion. You apply your row operations or adjoint method and you find the inverse, which will take a lot of time. You can find X inverse in just blink of an eye, because so what is a orthogonal matrix? That is one reason. Another reason being, it always preserves the angle between the vectors, and you apply the orthogonal matrix to it. You have say AV2 over here. If theta is the angle over here, here also you have the same angle. That means angles are preserved, and the length of the vectors are also preserved under the orthogonal transformations. Okay, so these are the two main reasons why in animation industry also, or whenever there is some transformations are going on, people prefer orthogonal matrix. Okay, so yeah, we have this as a singular value decomposition for a given non-rectangular or a non-square matrix. Now this is one way of looking at the singular decomposition. Another view of looking at SVD. See, you have studied, or you have seen eigen decomposition, or you can say diagonalization. There what we do, we write any square matrix A as a product of three matrices P, D, P inverse. Or I can write this as AB is equal to PD. So what this is doing, like A, P, say V1, V2 up to Vn. These are the eigenvectors, and this is my P over here again, V1 up to Vn, and my D is lambda 1 up to lambda n. So what this is doing is, sometimes people also say that eigen in its sense basis to, okay, let me not use this phrase because one can have zero eigenvalues. Let me erase this. Let me just tell you this geometrically what I want to convey to you. What I want to say is, if you are in Rn, n-dimensional space over here, and if you take a vector over here Vn, you look at its image, so A times P. So if I take A times V1, what is the image? It is some multiple of V1. So lambda 1 into V1, that is the first column over here, and this is the first column is AV1. I'm having lambda V1 over here. If I take V2 over here, I am having here lambda V2, image under A of V2. And good thing is, suppose, no, okay, so this is what it plays with the single basis. What I want to say over here, in eigen decomposition, we play with the dual basis. We play with the dual basis. And how that is, how you can visualize that? My A is what? U sigma V transpose. If I multiply by V on both sides, I get AB is equal to U sigma, because V transpose into V is identity matrix. Okay. So what is happening over here is A, I'm applying to the V matrix, which is consisting of some vectors, U, which is consisting of some vectors, and sigma, which is consist over here, 0, 0. So what is happening over here is, if I'm having V1 over here, its output is AV1, which let me call it as a U1. If I'm taking V2 over here, which is not in the span of V1, and I can always actually assume this as orthogonal. Why I can always assume this to be orthogonal? Thanks to Gram-Smith process. Once I have a vector V1, you take a vector V2 which is not in the span of V1, and one can always use Gram-Smith process to get orthogonal vector. Once I have here AV2, which is my U2. Question is, are this orthogonal? Answer is yes, because my U matrix is also the orthogonal matrix. So the vectors I'm getting over here is they are also orthogonal vectors. So it sends orthogonal vectors thing to look over here. Okay, and usually writing U1, let me call C. Normalizing means what? The length of the vector is 1. Again, here also the length is not 1. I will normalize it. So sigma to U2. So AV1 and so on. So this is another way of looking at the singular value decomposition, that it helps us to send the orthogonal vectors in n-dimensional space to orthogonal vectors in a different dimension. Okay, Rm. In eigen decomposition, we are going into one world to another different world of different dimension. So there is another very important, you can say theoretical, I would say theoretical importance. Being mathematicians, we should also look for the theoretical importance. Engineers, they always need practical importance, but we should never ignore. So SVD, one is in the form of a decomposition, product of 3 matrices, and another view of looking into orthogonal vectors. Okay, so yeah, so we have seen this. Now question is how to find U, sigma, and V, right? Because ultimately we should have this matrices. So answer is very easy. Suppose if you have a matrix which can be written in this way, then question is, what are these matrices? So answer is, what you do is, you first get U sigma V transpose into U sigma V transpose. And now we know by the property of transpose, this is V transpose into sigma transpose into V transpose. Our identity matrix V transpose, U transpose, sorry. Okay, so what I'm getting is, if I consider A transpose, I'm getting U sigma transpose, which is my square matrix. Moreover, this is a diagonal matrix to be precise, and this is U transpose. And my U matrix, so I can also. So what is this? Now we are coming back to the world of diagonalization. Okay, so to solve SVD, one has to go to the world of diagonalization. Okay, now the question is, does A transpose, that means can I write A transpose as a, can I diagonalize A transpose? That is what the question is, and answer is yes. For that, we should be thankful to the spectral theorem. Theorem says any symmetric matrix is there or not, but anyways, or any symmetric matrix, or even if we take positive semi-definite, this is indeed positive semi-definite. Okay, so in our case, is A transpose a symmetric matrix? Answer is yes, because by property we know that this is A transpose, A transpose, A transpose, which is A into A transpose. Is this positive? Is positive semi-definite? If X transpose AX is greater equal 0 for all vectors X, right? In that case, we say that our matrix X is positive semi-definite. In this case, answer is true, because what is X transpose A transpose X? I can write this as A transpose X. But what is this? This is nothing but my norm of A transpose X, which is always greater equal 0 by property of norm. Okay, what is transpose X? Which is nothing but actually X dot product X. Okay, so this is nothing but norm of X, A transpose X, which is greater equal 0. So our A transpose is a very nice matrix. It's a vector theorem. I know that A transpose can always be decomposed as U D E. So whenever we have the conclusion is, whenever we have A, the first step you find A transpose. This matrix, you find the eigenvalues and eigenvectors for this. One can also normalize the eigenvectors if they want orthonormal. So therefore, we get the matrix U, we get the matrix D. What is my D? If you compare with here, your D is nothing but sigma transpose, right? Your D is nothing but sigma into sigma transpose. Let me suppose if my D is lambda 1, lambda 2, for example, this is my say sigma 1, 0, 0, sigma 2, sigma 1, 0 transpose is the same thing. What I'm getting is, I'm getting sigma 1 square as lambda 1, and I'm getting sigma 2 square as lambda 2. So from here, we got U. What are the singular values? Your singular values are nothing but the positive square root of the eigenvalues. So if we are taking the square root, we should be careful, because if this is negative, then this will become, does this exist? Is this always non-negative? Answer is yes. Why? Because if you see a theorem, symmetric matrices have real eigenvalues. Okay, proof is very easy and important as well. So symmetric matrices always have, and thanks to this, because of this, this is non-negative, and therefore this is non-negative. So my sigma i's are always greater equal 0. They are nothing but the square root of the eigenvalues, and one can find the matrix U by diagonalizing, which matrix? By diagonalizing A transpose. So once you do A into A transpose, one can always have the matrix U and the matrix sigma. Now question is, how to find the matrix V? How to find the matrix V? Any wild guess? To find U, we took the help of A into A transpose. Now to find V, what do we do? Well, the answer is, we take help of A transpose into A. And by the similar argument, my A transpose A is symmetric, and and positive semi-definite matrix. And actually, let me actually find out for you. So this is A transpose means U sigma V transpose. And this is nothing but V sigma transpose sigma V transpose. So again, the same thing. This is my diagonal matrix consisting of sigma I square, and this is my orthogonal matrix. Does this exist? Yes. Again, thanks to spectral theorem, we know that A transpose A has a orthogonalizable, and therefore this V and V transpose do exist. I's also exist. Okay, so if you want to find an A transpose A, your job is over. Okay, so that's all about summarize the between. How to find SVD? Once you have A, U sigma V transpose, the step 1 you find A into A transpose. You will get your U and sigma. In step 2, you find A transpose A, and what you get is your V, and again sigma. Okay, these are same. No need to worry. I will tell you why. So once you have this, one can always have this decomposition. Why one can always have? Because this thing always exists. Given a matrix A, transpose always exists, product always exists, and it's a symmetric matrix. And because of symmetricity, we know that it is always orthogonally diagonalizable. Similarly, given product always exists, therefore these two matrices are orthogonal. Okay, so let me take one example for you. You will have a better picture for this. I think. Am I going very fast? I don't know. Is the speed okay for you? And usually in workshop, people are little hesitant to reply. So let me take a simple matrix. 1001, 1001. Okay, so this is a matrix of order 2 by 4. Let's go for step 1. What is A into A transpose? 1001, 1001, 1001, 1001. So the answer will be 2002. Good. It's a diagonal matrix. Great. So our job is done. You can always say the eigenvalues are 2, 2. It's a diagonal matrix. So your one vector is 1, 0. My A transpose is nothing but 1001, and the diagonal matrix, and then the inverse of 1001. Are my sigma I, my sigma 1 is square root of the eigenvalues. This matrix over here. Great. So we got sigma 1, sigma 2, and my U matrix. See, my A is the matrix of order 2 by 4. So from here one can realize my U matrix will be a matrix of order 2 by 4, and my V matrix will be a matrix of order 4 by 4. Okay. So yes, we do got our U matrix of order 2 by 2. Here we got sigma 1 and sigma 2. Now, as I said, what do? We find A transpose into A. What is A transpose? 1001, 1001. Intentionally, I'm taking this simple example because calculations will be easier. Otherwise, I will keep on doing calculation and you may go asleep. So that's the reason. So this is what uh, 1 0. Let me know if there's any calculation error. 1001 0101 1010 0101. So by A transpose A is a matrix of order 4 by 4. Now one has to find the eigenvalues for this. So let us try to find the eigenvalues. Let's set this to be 4. Our matrix was 1 0 1 0 0 1 0 1. Okay, so this was the matrix, and what did we get? We get over here as 2200. So the eigenvalues came out to be, my lambdas, they came out to be 2200. So what will be your sigmas? 0 0. Okay, and what is my vector v? My v is nothing but, yeah, so my v is nothing but, for 2 it is 1010, then 0101, then -1010, then 0 -101. Great. So we got our sigmas. Now see, if you observe, for A transpose I got only √2, whereas here I got extra eigenvalues, similar values 0 0. We will see how to represent, not to worry. And my A matrix, which was 1 0, it can be written as U matrix, which was 1001. My sigma matrix, which was 2 by 4. So here √2 0 0. Then here you are having B transpose. Okay. So and let me normalize it and let me take the transpose. So 1 by √2 0 -1 by √2 0. Second row was 0 1 0 -1. So now this will be 0 1 by √2 0 2. My third one will be 1 by √2 0 plus 1 by √2 0, and the last is 0 1 by √2 0 1 by √2. So this is my U, sigma, and V transpose. Okay, and this is the singular value decomposition for the matrix A. Okay, so you can see it's very simple and smaller order. So yeah, one can always use the calculator, or we can, if you have this course as a, if you have a practical for this course in your college, then one can always tell the students to for this. Okay, so yeah, this is one important thing. Now one observation. Suppose your A is a matrix of order, say 5 cross 9. Okay, your A transpose will be the matrix of order 5 by 5, and your A transpose A will be the matrix of order 9 by 9. So here you will have how many eigenvalues? Lambda 2, lambda 3, lambda 4, and lambda 5. And here you will have lambda 1 to lambda 9. Now, when you take the singular value sigma, okay, sigma 1 will be square root of lambda 1 and so on. Sigma I will be square root of lambda i's. One thing to observe here, one could have asked me that why, since we got root 2 root 2 0 0 and 2 root 2, okay, then here why did I wrote root 2 and not 0 0? Because as I said, we follow the convention, we take into the non-decreasing order. Okay, so if the root 2 was bigger than 0, that's why I took. Okay, now here also, here you are having 5 eigenvalues, here you are having 9 eigenvalues. What you do is you take the square root of lambda i's and you always choose the sigma i's in the non-decreasing order, sorry, non-increasing order. Okay, that's one thing to observe. And moreover, what I want to say is non-zero eigenvalues of A transpose will always be same as the non-zero eigenvalues of A transpose A. So you're not going to miss any eigenvalues over here. Okay, तो zero में होगा तो जो भी difference आएगा zeros थोड़े ज़्यादा रहेंगे, so that won't be a much problem for you. Okay, but what is important is, this is important, you always choose in non-decreasing order and try to fit the singular values over there. Okay, so that was one thing. Now there's one more before going to the real world application. Let me tell you one theoretical application. One I already told you. That it sends orthogonal basis to orthogonal basis. Now it also helps us to find the basis for very 4 fundamental subspaces. Would anybody like to comment? What are the fundamental subspaces that we usually study linear algebra? There are 4. Just to give you the answer. Any answer? What are the 4 fundamental subspaces we study?
Hello.
Hello, yes.
Sir, system of linear
equation we write in the matrix form.
Yeah.
And once you have a matrix form, we look for 4 nice subspaces. That for example, we look for row space. Yeah. Then
null space.
Yes. Let me write the notation wise. Row space of A, space of A transpose, which we call as the left
null space.
Left null space of A. Why this 4? Because they have a very nice relation. What is that nice relation? The relation is, if I having suppose, let me say this is the space of A is orthogonal to row space of A. Okay, they are always orthogonal. This is my matrix A. Then we go to the column space of A. And column space of A को क्या orthogonal रहता है? तो column space of A. Okay, so because of this nice relation, people are usually interested in these 4 subspaces, and they're interested in the basis and the rank and the dimension of all these subspaces. The good thing about SVD is one can tell using SVD, one can tell the basis for this subspace. That's why people usually find the SVD. Once you have the SVD, you can directly tell what are the subspaces. Let me tell you how. So my A is a matrix. So let A be a matrix of, say, rank R. One more thing to observe over here is, in diagonalization, we know that if my A is P D P inverse, then rank of A is same as rank of D. Similarly, in SVD also, if my A is written as U sigma V transpose, then my rank of A is same as rank of sigma. Okay, and sigma being, you have the on diagonals, you have sigma i's, and otherwhere is 0 everywhere. So ultimately, it is nothing but the number of non-zero singular values. Okay, so this is again a very important observation. So once we have, so similarly, we want to find the rank of a matrix many times. Again, going by row operations might take a lot of time. You simply look at the number of non-zero singular values, and that will be the rank of the matrix. Okay. So that's also one of, this is same as that of diagonalization. If I take the determinant of A, it is product of eigenvalues. Similarly, I can do the same thing in SVD. Okay, in SVD, if my A is a square matrix, then U sigma V transpose. Now all of is determinant of U, determinant of sigma, determinant of V. U and V being orthogonal matrices, its determinant is always non-zero, but the product of singular values. Okay, so from here also one can say A is invertible if and only if all similar values are non-zero. Okay, so there's another property. So I'm mixing up the things. So this is also a property that one should look for. Okay, where were we? Okay, we were at this fundamental subspaces. What are the bases for row space, column space, null space, and the left null space? You can recall we started with this different view. What I'm saying is, I know that my A V is U sigma. Okay, that means A V1 V2 up to Vn is U1 U2 up to Um into sigma 1 sigma 2 sigma n, or let me suppose if R is the rank, and then rest will be 0. Then what we're getting is AVI is sigma I. So out of this, some of the vectors will have the image 0. So some vectors will have the image 0. So only till R vector I will have AVI equal to UI, or the will be the basis for null space of A. So you look for the first R vectors, and those will be the basis for the 2Vn. R, where R is the rank, okay, where my R is the rank of the matrix, because I'm having R non-zero singular values. Then what about the column space of A? Again, you take U1, because the rank is R. I will have the R vectors over here, and the remaining null space of A transpose will have UR plus 1 to UN. So you can see, once you have SVD, you can talk about the invertibility, you can talk about the singular values, you can talk about the basis for the row space, null space, column space, null space of A transpose. You can tell the dimension. One can involve rank nullity theorem to get the dimensions, and plenty of things can be extracted. What I want to say is, from SVD, one can extract many. Yeah, SVD is kind of important. Okay, I think I'm going very fast. I have reached to the properties section, or I would say the application sections. So we have seen theoretical applications. Now we are going to see the some real world application. But for that, let me give you some one observation. Okay, the observation is, see, you have a matrix A, U sigma V transpose. My A is a matrix of order m by n. My U is a matrix, so this is my, say, let me write a smaller way. U1 is a vector, okay? I'm just using a smaller bracket. U1, U2 up to UM. Then I'm having sigma. Say the matrix is of order R, and the rest everything is 0. And here I'm having V1 transpose, V2 transpose. Okay. Now, if you multiply this, what do you get? If I multiply first column sigma and this first row, what I get as A is equal to U1 V1 transpose sigma to U2 V2 transpose sigma 3 U3 V3 R UR BR transpose. Okay, so I'm able to write A. So observation, your A is expressed of R matrices. To be precise, sum of R rank 1 matrices. That's a very important point to observe. Each of, see, this is a matrix, this is a number, this is a vector of order m cross 1, and this is 1 cross n. So this is a matrix. My sigma 1 U1 V1 transpose is a matrix of order m by n. Okay, in general, all of them is running from 1 to R. All of them are matrices of order m by n. Lemma, if x, then x y transpose is a rank 1 matrix. Okay, very easy proof. My x bar is suppose x1, x2 up to xn. My y bar is, say, y1, x1, y1, x1, x1, y3, x2. This was the question was asked to me in an interview during my PhD intern. X2, y3. Luckily, I got the proof. So, so this is my x in y2, x in y3, x in yn. Now, from here, can you see it is of rank 1 matrix? Anybody would like to comment on this? That why this is of rank 1? One can have a nice observation actually. Any guess? This is y1 times x bar, y2 times x bar, y3 times x bar, ym times x bar. Can you obtain this column from this column? Answer is yes, right? Because you multiply this by y2 upon y1, you get this matrix. Can you obtain this column from this column? Yes. So one can always obtain one of the columns from other columns. And so there, I mean, one can. So there's a rough idea. I think I should. Therefore, the rank is 1. And because of this reason, 1 matrices. Okay, and that's the beauty. Because of SVD, R, and if X and Y are rank 1 matrices, so some basic stuff that one should know are rank 1 matrices, then X plus Y is a rank 2 matrix. Okay, and therefore your A, which is sigma 1 U1 V1 transpose plus sigma transpose plus sigma R UR VR transpose, all of this of are rank 1, and therefore it is nothing but the rank of the matrix A. Okay, so this is a very important observation that one has to look for when they are playing with the singular value decomposition. Now we look over here. Now comes the image processing into the picture, or image transfer, you can say, or image compression, whatever word you like, you can take it. See, this is called as the decomposition of A as a sum of rank 1 matrices. Now, if I don't take the last matrix over here, then what I will say, my A is approximately sigma 1 U1 transpose plus sigma 2 U2 V2 transpose plus sigma R minus 1 UR minus 1 VR minus 1 transpose. That means A can be approximately, A is approximately sum of R minus 1 rank 1 matrices. Similarly, suppose if you want to write it as a sum of R minus 2 rank 1 matrices, we will go up till U R minus. What I'm saying is, if you take sigma 1 U1 V1 transpose, you will not get the complete matrix. You will only get transpose. You will again not get the complete A matrix, but you will be a little bit closer to the matrix A as compared to sigma 1 U1 V1 transpose only. Again, if I take more matrix, I will come little more closer to A. So this is my first packet. You can look in this language. This is my second packet, third packet. As I keep on getting the packets, I'm approaching closer and closer to my matrix A. Okay, and that's what happens when a data is, or when an image, satellite sends an image to Earth. Okay, for example, this is the idea. Okay, just keep this idea in mind. One can always approximate, or one can send the data in packets. Okay, so example, suppose there is a satellite which takes a picture and it wants to send the photo to Earth. Okay, so you have a 2D image over here. As I said earlier, the image is an RGB color code, or one can also have a gray image color code. And suppose you have a picture of pixels, 1000 by 1000 pixel size. That means what? How many squares? Here is one color that is given some another color code. Okay, so you are having this small squares. How many squares? We are having 1 million small squares. And each color has a color code. Okay, each color, and you have a converted into the pixel matrix using that color code combination. In Python, there is a direct command which one can get that in Python. Yeah, but anyways, so there are squares over here, and as I said earlier, there is a very in the data in between, because when the data, there is no wire, there is no that much of communication, like the satellite is in the space, so there are high chances of losing a data. So therefore, it is good to send the data in packets. So what we do is, this is my matrix A. You have the matrix as summation of sigma I, ui, vi transpose, where I is from 1 to R, where R is the rank of the matrix. Okay. Now what you do is, instead of sending this much entry, what you do is, you first see sigma 1 u1 v1 transpose. That means how many entries are there in u v1? 1000 entries here, 1000 entries here. So you're sending 2001 entries. तो इससे थोड़ा सा picture दिखेगा. As I mean, when the data is being sent or photo is being sent, it always, the first image is always a blurred image, and slowly you keep on seeing the clear image. That means blur image था मतलब पहले it has only sent this much of the data. Then since this is what my u sigma v transpose. Okay. So वो software does that decomposition. Then next lot में next packet में it this much data. So कितने हो गए entries at one shot. I am sending the entries in this form 2001. Suppose I am sending 20 datas, 20 packets. Again here 2001. So ultimately how into 20. So kind of you can say approximately I am sending 40,000 data points, or the data points. Okay. Here there were 1 million, but here I am sending only 40,000. You see the comparison. 25 is to 1. So that much comparison we are doing, and अगर यहाँ से इतने से अगर इमेज ठीक मिल गया तो we will stop. We are not worried. उसके बाद भले डेटा आता रहेगा कि which photo it has sent. Let me show you this with the help of a photo so that it will be much more clear to you. So this was the paper which I got online. I was going to do Python code, but time mila nahi, so I couldn't do it. See, here is a picture of a leaf. Okay, so it's a very high definition picture of a leaf. Now you see over here. This is the first photo it has sent. This is the second photo. This is the third photo, 4th, 5th, 6th, 7th, 8th, 9th, and so on. This consisting of, you can see, the number of singular value is only 1. You can see over here, for this only one singular value, U1, V1 transpose. Can you see what I'm writing on the pocket? Thanks.
Yes, sir.
Now this is what this consists of, this plus this, sigma 2 U2 V2 transpose. As I said, they keep on sending the data in packets. Now here they have taken 5 singular values. This is for 5. Here they have taken 10 singular values. Here 15, 18, 24, 30, 35, 60, and now you see the last two picture. There is hardly any difference. Let me just zoom it out for you. You see from the naked eye, you cannot see that there is a huge difference. One can easily predict what is that. There is a leaf, and you see the difference. 120, huge difference. How many similar values are not considering? You are not considering 560 similar values, 680 minus 120. This much you are excluding. Similar value 560 rows of V transpose. All this you are excluding, and still you are getting the same thing. Like my friend, like when we click the photo, now everyone has a good photos now, good camera nowadays with 48 megapixel, 50 megapixel. I don't know whether you observe photo through WhatsApp. Then image quality little bit it decreases. If you're a good observer, you will realize that, and that's why my friend told me that don't send me through WhatsApp. You upload it on Google Drive and then link. But when you of space, instead of that, it sends this image. You can see it's almost same, right? There's hardly any difference. So why to take so much of space and send the exact the same image? And this is called as a low rank approximation. Linear algebra भी कर पढ़ा हो. This is called as a low rank approximation. You fix one threshold value, and your job is done. Okay, so and let's blur because it uses this technique of low rank approximation. Okay, now if someone says you they have the color image over here, you can see this. This is the red, green, and blue color over here. This is the first shot. This is the shot when only one singular value is used. Okay, the first. In second one, 10 singular values. Means 10 rows of U, 10 rows of V transpose, and 10 singular values. This is for 25, and this is for 100. Okay, so as you can see, the 100 matlab I hope you are getting. Matlab I am taking 25 means what? I am taking summation sigma I, Ui, Vi transpose. I is running from 1 to 25, 1 to 100. See here are the two photos. The original image on the left and the compressed image. From the naked eye, you can directly say, "Arey, dono same hai." Values, they approximately use 50% of the original storage space. There are actually 574 singular values, but I is from 1 to 100. Here I is from 1 to 574. So you can see one can save lots of space through this. Okay. इसलिए जब हम मैंने compress also using WinZip or WinRAR, when the images get compressed, this is what nice example. Those who are interested, they can say this. I'll just share with you. The paper is SVD, Application to Image Processing. Okay, Journal of Undergraduate Research. It's a nice paper for if you want to see it. This is one more example of noise cancellation. Okay. Sensors are vulnerable to noises, and sensors, we know that. So there might happen that the readings get हमेशा ignore करते हैं. From this example, the singular values, better the picture, right? Because we always, as I said, the nomenclature, don't forget the singular values in non-increasing order. Okay, sigma 3 greater equal, and हमेशा हम stores lot of information. I heard this somewhere. I'm not sure where I heard, but it says that the largest eigenvalue, the vector corresponding to the largest singular value, it stores around 60% of the data, or 50 to 60% data. The largest eigenvector, principal component analysis, and all those topics in machine learning comes into the picture. That's one thing. So larger the singular value, larger is the data stored, and as you keep on decreasing the singular value and you take the corresponding singular vectors, then the information keeps on decreasing. Therefore, people usually ignore the singular values, less value. Okay, so here you can see nice. Okay, here also is a dark color over here. So you find the SVD and you ignore those rows and columns of U and V transpose with very small singular values, and you can see this is a denoised image. See, now this is a much better than the scanned one, than the scanned image, because we are ignoring the very small singular. They don't contain much of the information. The main information is always for the larger eigenvalues. Sorry, for the larger singular values. Okay, so the image compression and the image transfer. So that's how the images are transferred in packages, and I hope now it is clear, and why it gets clear and clear once we have more of the data. Okay, so that was one thing. There's one more place where it is used a lot. There is something called as a condition number. Before going to another application, there's something called as a condition number, which people always want to look for it. I think the notation is rho or something. Rho is nothing but the maximum singular value upon the minimum singular value. This is called as the condition number of a matrix. Called as what? Condition number of a matrix. About the singularity of the matrix. How does it tell you? See, lower the singular value, that means larger the condition number, larger the condition number implies smaller the singular value. Okay. Well, suppose if you have a very big matrix, A is a matrix of order whatever, say 5 billion or say 50 billion cross 50 billion. Okay, and your computer is finding the singular values, and अगर तुम देखते जाओगे कि if your condition number is keeping on increasing, मतलब what, your sigmas, they are decreasing. That means what, this is approaching to zero. When this will go towards infinity, or when this will keep on increasing, when this will keep on decreasing, and they are non-negative, that means this is approaching towards zero. That means as it keeps on increasing, as rho keeps on increasing, yes, I would say the chances, okay, the chance keep on zero, and we know that the matrix is invertible if all the singular values are non-zero. Okay, so if this is increasing, that means this is approaching towards zero. That means, I mean, this is another reason that computer scientist people, those who work in computation, they are interested in the condition number of a matrix, because it tells you whether the matrix is invertible or not, or how far it is up. Yeah, so if you study sometime condition number in future, this is the important point that one should convey to students. Okay, it tells you about the singularity of the matrix, which is a very important thing that one should take away from the condition matrix, from the condition number. Okay. Yeah, let me tell you one last point over here. The last thing is about the least square method. I assume that when you have studied regression, this. See, before coming to this, why least square method is important? Why do we use it? So if you have some data points over here, everyone knows what is the idea about regression. So if you have some data points like this over here, what is your job? Your job is to find the best fitted line. Okay, your job is to find the best fitted line or the best fit curve you want to find. Okay, why? So that you can do the predictions or forecasting. Okay, so that once you have the data till here, question is now if I take, so you want to find the best fitted curve, best fitted distance. Sum of distance should be minimum, right? This is what you study. Question is how to find that. That is one question, but we will see how. I mean, I will give the answer to that question. But for that, I will need the concept of pseudo inverse. SVD helps us to find the pseudo inverse of the matrix. What is pseudo inverse? If the matrix is not invertible, one can find not the exact inverse, but That's why the name pseudo inverse to it. Okay. So, and this is for non-square matrices as well. Okay, not only for square matrices. Invertibility we only study for square matrices, but when you have a non-square matrices, we do not have the concept of invertibility. That's why this pseudo inverse may be a matrix of order m by n, and suppose your A has a singular value decomposition U sigma V transpose. Then the pseudo inverse ka notation is A plus, it is U sigma V transpose plus, this is V transpose plus sigma plus U plus. But my V and U are orthogonal matrix, तो वहाँ पे से the plus sign will go away. So this is what the pseudo inverse of the matrix is. It is V transpose sigma plus U, sigma plus into U. Okay, what is sigma plus? My sigma plus is nothing but you take the transpose of sigma and you take 1 upon the singular value. If the singular value is non-zero, and 0 if the singular value is null. What I want to say is, if my sigma is say 200 300 0000, yeah, this is my sigma. And what is my sigma plus? The pseudo inverse of sigma. You take the 3 is non-zero, so 1 by 3. Take the transpose 0 0 0. Then second row 0 1 by 2 0 0 0 0. This is 0. When the sigma is 0, you take 0 only. Okay. So this is the pseudo inverse of sigma. Okay, it's easy. Just take the transpose. Two condition. Take the transpose. Second, may the diagonal part 1 by sigma when sigma non-zero, 0 when sigma is 0. Now this is the concept of pseudo inverse. Okay, good. Now let's go to least square method. Now what happens in least square method is, as I told you, you have the data points over here, or the data set is given to you. You want to find the best fitted line. Okay, instances this error should, if you have the data points xi, yi, this is my x, this is my y. Okay, these are my, these points are xi comma yi's. Okay, so this is the data set you have. And what is your job? Your job is to find the best fitted line. Best fit line. That means say ax plus by equal to c. Best fit means what? When I substitute, we want to find this line. We want to find this line so that when I put on this line, this is the line, right? And when I substitute this xi is yi's in this on this equation, this error should be minimum. Means what? If I take axi plus byi minus c square and I sum it up. Okay, this error, so these are the errors. If x and y, xi, yi is on the line, then it satisfies. If not on the line, it is beyond, away from the line, then you will using optimization techniques. You have the partial derivatives, you take the derivative, equate it to 0. Again, by teaching calculus, if someone asks for application, this is a very nice application. You can say it helps us in optimizing the stuff. Okay, so our job is to minimize this so that this should be close to 0. Okay, this is same as I want to minimize what I want to minimize xn plus B minus C. Norm 2. Norm 2 means what? You take the squares. Okay. So this I want to minimize. That's what my task is for every ABC. Okay. So you want to find your ABC. So that this is a minimized thing. Now also, as one can observe, you can write this in the vector form, matrix form as well. What you do is you take your A as x1, x2, x3, so on, y1, y2, so minus 1, so on. A, B, C. So ultimately, I am rewriting this. I want to minimize AX. This is what I want to. So ultimately, this is what your optimization problem is, or this is what your least square to minimize the distance. Okay. So let me just formalize it. So here is the question for you. The question is: suppose we have AX bar equal to B bar. A and B I told you already. You can take on the right hand side, not an issue. Close to the B bar. Last time the B bar was 0, my right hand side became 0. Need not, my X bar belongs to Rn. How to minimize this? Once I minimize this, my X bar is called as what? It is called as the least square solution to the equation AX bar equal to B bar. So how? And that's where the concept of pseudo inverse comes in. See, this is not a square matrix. This is a Mendler matrix. One standard way that people usually study is by taking the transpose. The standard way is you have AX bar equal to B bar. You take a transpose on both sides, and your X bar. Your now this is a square matrix. See, always keep this in mind. This is a very nice. Always multiply with the transpose. It becomes a square matrix. And if this is invertible, this is the solution to your problem. If it is invertible, okay? If invertible, then this is the solution, exact solution you can say. No need to find the approximation also you have. What if A transpose A is not invertible? In that case, what to do? Therefore, pseudo inverse will always help you. Okay. Usually, when I have seen the syllabus of few colleges, they always go by this way, but then they never cover this way. Okay. Maybe because SVD is not there, it's okay, not their issue. But yeah, usually these things happens. Yeah. So how to find it? The answer to this is a very. Suppose A and B bar are two matrix and vector. A is a matrix of order m by n. B is a vector of order m. Okay. Then X bar A pseudo inverse B bar is then X bar A pseudo inverse B bar is the least square solution to which system of equation? To AX bar equal to B bar. That means what? Your X bar is nothing but U sigma V transpose plus, which is nothing but V sigma plus U V bar. So you simply find the singular value decomposition, and once you have this, you take the pseudo inverse of sigma, and what you get is the square solution. So yeah, I hope these examples are clear. These were some more examples which I came across. As you. Noise removal, I told you how noise algorithm, it is used a lot. This is the classification that we have done. It also helps in the handwriting classification. Okay, handwriting, this also just remember. Whenever you want to classify in machine learning, you always go for the classification algorithms. Okay, so whenever you want to classify, like see, whenever you upload something, you want the what it is written. But he has just now they put into the production of this image. You can upload the image and it will read the image and it will give you the answer. Or even the Google Lens also have this homework facility. You just scan the question, it gives you the answer. It's not that good, Google wala, but okay, is there. What to do is, like, suppose a 6 is written like this, like this, like this, like this. To okay, so it take the system take this as an image. Again, it will have this. It is nothing but consist of the squares. It has the color code. Okay, suppose this is a k cross k image of size k cross k. So total how many squares? Total you have k squares. Okay, then this is the first image 1 2 k square. इसको हमने first में रख दिया. This is my second data set. Again, this is a k cross k image. It will have k square as the second row of the matrix. Take this as a third image, 6, 7, 8. So you have 8 rows with k square columns. Okay. Okay. The same kind of this technique, ये जो technique है ना यहाँ पे, this same technique is also used. So when you take the many people nowadays, you have by just the phone reads, I mean, with your face, right? Face unlocking. So when you buy a new phone or it print unlock the phone using finger, you have to do it like, and then anytime you keep the finger, it's in data sets, the phone, the software is capturing. Even for the photo image, like suppose when I'm buying a phone, at that time I may have a very little beard. I'm at home, I have done the clean shaving, and the background is a wall. Still, it will unlock the phone. So, do you think that it exactly matches? No, it doesn't exactly matches. Again, some threshold value is put. Till that only it matches. Once that matching is done, it will stop matching the data. Let's say U1 V1 transpose plus U2 V2 transpose. It will keep on matching once after till certain limit. Once it is matched, it will not match further, and your phone gets unlocked automatically. Okay, so for face recognition also, for recognition, whatever the spelling is, it for that also it helps you. Okay, those are more interested on this, they can go through this. They can icon face decomposition. Those are more interested, they can go over here. See, different faces are taken. everywhere you can see the background are different. Somewhere the photo quality is also not good. But then, as I said, this is a K cross K image. That means there are K square small squares, and then you arrange it as a row wise. Once you arrange it at row wise for all the data set, you have a matrix, and then you compute the mean for each column of the matrix. Component analysis. That means you take the eigenvector for the largest eigenvalue or the singular mean, the covariance matrix, blah blah blah, and you keep on algorithm works. Okay, so yeah, I think we have seen that it is used in image processing, image compression, noise cancellation. Electronics people use this a lot. Signals में हमेशा noise रहता है. Again, this is used then least square method. All these were very practical examinations, applications which engineers are interested. Along with that, we saw how to find the basis for fundamental subspaces. We also saw how it helps to send an orthogonal vectors to orthogonal vectors. So it's a two basis decomposition. Okay, another good diagonalization is a single basis decomposition. Okay, whereas this is a two base, because here you have U and V, two different matrices, one matrix which is U. Yeah, I think I should. Yeah, I think I should stop now. I have told you many information in this. Yeah, the 20 minutes are there, but I think yeah. I think this is where I should stop. If anyone has any questions on this, or if you want any extra information, you can please ask. Any questions or anything? Any comments? Was it too fast? I will take care in the next workshop. Or yeah, any justification for any of the comments which I made? Thank you, Pankaj. Thank you, everyone. Yeah, I think okay, Sandeep sir. If I hope it's okay if I stop 15 minutes earlier. Sigma and summation range. Sorry, I didn't get the question. Sigma and summation range as in? The summation of sigma I ui vi transpose. We take, I mean, whatever I'm predicting is, we write A as a sum of R rank 1 matrices, and we don't take all the rank 1 matrices, all R rank 1 matrices where R is the rank. We keep the value, we take the value in packets, sigma 1 u1 v1 transpose, plus we take sigma 2 u2 v2 transpose. If these two rank 1 matrices are giving me the photo or what I mean, that's why it is very useful. No need to wait till all the data comes in. I can't see any other question in comment section. Okay. I will share the PDF also if somebody wants, then Sandeep sir will share with you. Summation working present. Okay. Thank you. Thank you. Sure, sure. Thank you. Thank you. Thank you, everyone. Yeah, just share with me also, Sandeep sir, if possible. I will take that as an improvement.